Hi, welcome back to Sam's Maths Lectures. Today we're continuing the series on path integration. Um, we're going to be still not quite at path integrals for sort of this video or the next couple really, but we're going to be doing sort of a brief overview of Fourier theory. And sort of the general idea of what we're going to do here is sort of moving between position space, so functions of x, and functions in momentum space. So if we have a sort of momentum k, then we're going to have sort of functions sort of g of k, and sort of expanding these functions of f as functions of k, because that sort of is going to make it easier for us to do certain things in quantum mechanics. So for example, kinetic energies are easy to calculate in momentum space, less so in position space. Okay. And so we're going to work in d dimensions, so d greater than or equal to 1 dimensions. We're not sort of worrying about space part and time part yet. That's not really important. D greater than or equal to 1 dimensions. And what we'll do is we've got sort of basis E1 to ED, orthonormal basis of C to the D. Okay. And what we'll do is we will define a lattice in our space. So, I mean, really, this is real space, not complex space. We're going to be going into complex space, but sort of position space is real, right? So we've got a lattice, capital X, and this is just sort of linear combinations of these basis vectors. So sum from I equals 1 to D. We've got the basis vector EI. We're going to have this sort of lattice spacing A, so the lattice points are each going to be spaced by this distance A, and then Ni, where Ni is any integer. Okay, so we've sort of got this regular sort of, in a line, it's just regularly spaced points in 2 dimensions, d equals 2. This is going to be sort of a grid. We've got a cube in 3D, or cubic grid, really, and it sort of continues to infinity. It's with these equally spaced points everywhere. Okay, and to make life easier, we're going to sort of impose periodic boundary conditions on ourselves. So we're only going to look at these functions in the set f, which is functions f from our lattice into, we'll do the complex numbers now, we'll sort of generalize later to any complex vector space, but for now, just complex numbers, such that for all points x and I equals 1 up to d, we want f of x to be equal to f evaluated at the next lattice point over in the ith direction. So x plus a ei. This is going to move us to the next lattice point. Well, not the next lattice point over, but n lattice points over. Okay. So let's say we've got this sort of regular grid, 1, 2, 3, 4, like this. What we could do here is, let's sort of be a bit boring and put n is equal to 2. Then if n is equal to 2, then the function evaluated here must also be the same as the function evaluated here, as here, as here. This is sort of d equals 2, n equals 2, that sort of thing. Now, obviously, as you can immediately see from this, we've sort of defined that, and then this point here, well, the value there is going to be the value here and here and here, and the value at this point is the value here and here and here, and so on, right? You know, the value, just to finish it off, I guess, the value here is the same as the value here and here and here. So we only need to know sort of the values in a small box to know the values everywhere. So what we'll do is we'll sort of impose, first of all, the fact that n is odd. It's just sort of useful for us. And so we see that if f is one of these periodic functions, it's fully defined and uniquely defined as well by its evaluation on just sort of a subset of the spatial lattice X, this sort of fundamental box X naught, we'll call it, which is sort of elements of the space lattice, such that all of their coordinates are sort of restricted between minus n minus 1 over 2 less than or equal to ni less than or equal to n minus 1 over 2. So in this case up here, if, well, we've said n is 2, which is sort of wrong, but let's say we've got 1, 2, 3. Pretend that this is sort of squarely spaced. Here we go. If this point here is 0 and n is 3, then we're going to go to minus 1 and plus 1 for both of our coordinates. So x naught is going to be these 9 points here. Okay. And we should probably note that down, that the number of points in x naught is n to the power of d, because we have d variables and they each can take n values. Okay. Now, that's good because it sort of tells us that this sort of f is finite dimensional and it has dimension. Simply n to the power of d, and we can see this by sort of imposing a basis fx, where fx evaluated at x prime is just the Kronecker delta of x and x prime. Okay, so it's 1 if they're equal and 0 if they're not. So we've got one of these functions for each x in x naught. So we've got n to the d functions, they form a basis. Okay. Now let's define a scalar product on f. And this scalar product will be given by f with g. It's going to be the sum over the points in the sort of fundamental box fx star gx. You could also say sort of when we later generalize this to sort of any complex vector space, we'll have sort of a vector at each point, and then it will just be the dot product of the vector at x from f with the vector from g, using the dot product on the other vector space. But we'll sort of talk about that more later. Okay. Now, obviously, in this basis, fx are an orthonormal basis, and that's been covered up by my face. Orthonormal basis here. And we could also, what we might do is sort of rescale this dot product. So what we'll instead do is we'll say, we'll put in an a to the power of d here, and then fx is not quite an orthonormal basis, but it is an orthogonal basis. And the reason for that will sort of appear later, but basically we're using the lattice spacing, and it's going to turn things into integrals later on. Okay, so let's look at sort of functions e to the I k dot x. So these are sort of naturally periodic functions anyway, in f, and for that to be periodic, we can sort of look at it and we can say, well, if we increase x by any sort of integer multiple of a in any direction, then we have to sort of increase k dot x by an integer multiple of 2 pi to keep this thing the same. And so this sort of imposes a requirement that k is equal to a sum from I equals 1 to d of ei, and then we're going to multiply it by an integer li and this sort of inverse lattice spacing, 2 pi over L, where L is NA, okay, and Li is any integer. And you can see that this will give us periodicity. Now we can do a dot product on this. So f of k primed is equal to f bar k, sorry, where f bar k is equal to this thing. So this will be the sum x in x naught. We've got an a to the d here, e to the minus I k dot x, e to the I k dot primed dot x. Okay. Now what we can do is we can obviously combine these vectors into one dot product in the exponent. We can take the AD out, and we can sort of write this sum over x's as just sort of a sum in each direction, and we multiply all those sums together. So we've got this sort of product over the dimensions, 1 to d, then a sum for ni goes from minus n minus 1 over 2 to n minus 1 over 2. And inside this sum, we get e to the 2 pi I over n, because remember that x has an a in it, and there's a 1 over a in the k's, and so those cancel, and we just sort of get left with the n. 2 pi I over n, L primed I minus Li times Ni. Okay. Now there are sort of two cases, and we can actually rewrite this again. E product I equals 1 to d, sum from Ni equals whatever to whatever, and we're going to call this whole thing here without the Ni alpha I. Alpha I to the power of Ni. Two cases. So the first case is that for all I, there exists some integer m such that L primed I minus Li is m times n, and therefore alpha I, if we sort of plug that in, alpha I is equal to 1, and so therefore each of these sums is just going to be ni equals minus n minus 1 over 2 to n minus 1 over 2, the sum over this. Alpha I to the ni is just the sum over the ni's of 1, and so that's going to be n, and so we get the dot product f bar k primed is n to the d times a to the d, which is L to the power of d. Okay. Or otherwise, there exists something where this isn't true. So there exists I, where basically L primed I minus Li is not equal to m times n. So alpha I is not equal to 1, but because L primed and L are both integers, we still have that alpha I to the power of n is equal to 1. And when we do this sum, this is just a sort of simple geometric series. Alpha I to the n, alpha I to the, sorry, little ni. Let's rewrite that. We do this, then what we sort of get as our sum, ni, remember, starts at minus n minus 1 over 2, goes to n minus 1 over 2. So we do the first term, alpha I to the n minus 1 over 2 minus, and then we multiply by the sort of geometric ratio to the power of n, minus 1, and divide by the ratio, minus 1. And this thing on top is equal to 0, and so this whole thing is 0 for that I, and so the entire dot product is 0. Fk primed is 0. And so we sort of see that unless k and k prime are related by this sort of integer multiples of n, then the dot product is going to go to 0. And so we can restrict our sort of reciprocal lattice, which was our set of allowed k's, which I didn't write it down before, but it was b, is equal to basically all of these sums. Where were they? Here, where we've got this e, I, li, 2 pi over l. Sum I equals 1 d 2 pi over l, li, ei, where li is an integer. Well, we can restrict that sum to sort of say, well, our basis doesn't take every k in B, it just takes a fundamental box of B, just like we had with X. So we just sort of need to look at B naught, which is k in B, such that minus n minus 1 over 2 is less than or equal to Li is less than or equal to n minus 1 over 2. Okay, and now we've again got an orthogonal basis where sort of the only time where this thing is allowed to not be 0 is if k and k primed are equal. So now f bar k, where k is in B naught, is an orthogonal basis. It's still not sort of a orthonormal basis. We haven't normalized the product, but it's orthogonal. And that will do for now. Okay. Now, sort of, if you've done any sort of Fourier theory before or solid state physics, you'll know that we sort of have more k's really that should be allowed. And we've sort of we've cut off our k's at some point. And that's because we're only sampling our functions f at the lattice points. So if we sort of do literally just one dimension, so d is equal to 1, and let's say that n is equal to 3 again. In fact, n is equal to 1. Then there is no difference between sort of a constant function, which is going to look like this, and so it's 1 at all the lattice points. So this is k is equal to 0. And the function cos x, so this is k, or it's a combination of k is equal to, this is l is equal to 1, so 2 pi over a. Right, because it goes back to 1 by the time we reach these lattice points. Again, if we sort of allowed n was equal to 2 again, just sort of for argument's sake, so that 1 and 0 are different, then we would be allowed another function. We'd be allowed this function, not that function. This hasn't properly gone below 0, but we'd be allowed L is equal to 1, because now n is bigger than this is n equals 2. Not n, L is 2, L is 1. Okay, but there's no sort of distinction between L equals 2 and L equals 0, because we only see things at the lattice points. We don't see this point in the middle where they're different. Okay. Now, using this sort of new reciprocal basis, we can say, well, if we have some function phi, we can express it as a sum over the reciprocal lattice in the fundamental box. And we sort of introduce this normalization. These phi bar k's are just the coefficients divided by L to the D, e to the I, k dot x. Okay, so this is just expressing phi of x in a new basis where phi belongs to f. And so then we can say that, well, if we sum over the fundamental box phi x e to the minus I kx. Now this is sort of where k belongs to the fundamental box. Again, this is sort of a rescaled dot product of fk and phi, f bar k, sorry. And so we know that that's going to sort of pick out the k is equal to k primed. If we sort of call this k primed, k primed, k primed in this one, then we sort of end up picking out that this is 1 over L to the D, sum over the k primes in B naught, sum over the x's in x naught, phi bar k e to the I k primed minus k dot x, and that's gone off the screen. But let's sort of move it. So let's move that down here so you can see it. And I missed part of the x. There we go. So that is now equal to this. But we know that this sum is going to introduce this delta with a factor of nd in it. And so we get that this is going to end up being AD, 1 over AD times phi bar at k, right? Because we sort of get this delta function. The Kronecker delta is going to come in here and it's going to pick out k primed is equal to k. That should have been a k primed. Yeah, but then we get the scaling 1 over AD. Or we could say that phi bar k is AD sum x in x naught 5x e to the minus I k dot x. And we could also call this, we can take this a to the power of d inside the sum, and a to the power of d is the lattice spacing in x, right? The points in this x lattice are separated by a. So we could also write this a is equal to delta x to the d, basically. Phi x e to the minus I k dot x. It's x in the fundamental box again. And in the same way that we've written a is the x spacing, the spacing of the k vectors was 2 pi over L. That's sort of what you increase by when you move by, when you increase Li by 1. And so we can sort of rewrite that other sum as 5x is the sum k in the fundamental box, delta k to the power of d divided by 2 pi to the power of d. We sort of got this extra 2 pi in there. Phi bar k e to the I k dot x. And I'd like to make sort of 3 observations here before we move on. So observation number 1 is that if phi of x is real, so phi x is phi x star, then that means just sort of by inspection of this formula here, we sort of see that, well, when we change phi x, we conjugate this, the k's are going to get sort of flipped around, and the phi bar k's are going to get conjugated. And so what we need is that phi bar k is phi bar minus k star. So we get this sort of almost sort of like odd and even functions where we introduce an extra minus sign. Don't like this shade of blue, so we'll change to this one. Observation 2. If phi of x is just a sort of scaled delta function, so 1 over a to the d, delta x with x naught for some vector x naught, then phi bar of k is just e to the minus I k dot x naught, just by sort of plugging it into our formula for phi bar of k. and we can then sort of get phi of x back. So a to the minus d delta x x naught is the sum k and b naught of 1 over 2 pi to the d delta k to the d e to the I k dot x minus x naught. Okay, and this will sort of turn into an integral representation of the delta function later on. Okay, and the last thing is by sort of looking at dot products. Phi dot product with phi is equal to a to the d sum x and x naught phi x star and phi x. The second phi could be a psi, right? We could do this for any dot product, but we're just sort of looking at the Plancherel identities, which tell us about sort of just the sums of squares or modular squares. And this is also 1 over L to the D sum over K in B naught phi bar K star phi bar K, just by doing the dot product of the FK basis vectors. So the problem we've got is that so far we've been working in sort of a discrete lattice with these periodic boundary conditions, and the real world isn't on a discrete lattice, at least not at the level we're going to be working. We're not worrying about quantum gravity or anything like that. And also we sort of have this problem of these periodic boundary conditions. We sort of don't want them because we don't really see periodic boundary conditions in the real world. Maybe on a cosmological scale, but we're not worried about that either. Okay, so the first thing we do is we take the continuum limit. Okay, so what we want is we're going to take a to 0 so that the lattice points in real space get infinitely close together. But we're also going to sort of take n to infinity in such a way that L equals an equals constant. So we don't want to sort of contract or expand our box. We want our box to stay the same, but we just sample at more and more points inside the box until it becomes sort of a continuous sampling. Now, what happens to things like the sum over delta x to the d f of x for x in b naught? Well, this is in this a to 0 n to infinity limit. This is just the definition of Riemann integration, right? It's sort of we sample at sort of more and more points, and we sort of look at the volume of each sort of point that we sample, and we end up with that this is going to go in this limit to the integral over this sort of fundamental box squared. The minus 1 in the end sort of disappears out of this. Obviously, this interval is going to be to the power of d because we're in d-dimensional space, so d dx f of x. This is basically just from the definition of the Riemann integral. While sort of our reciprocal lattice sums, so sums over k's, well, the k spacing is going to stay finite because that's based on L, not on a and n. But our fundamental box is sort of going to grow to infinity because remember that b naught was just restricting the coordinates to be less than n, but n is now going off to infinity. And so what we get is that a sum delta k d, and I'll include the 2 pi factor as well. It's just sort of conventional that these two things always appear next to each other. F bar k, well, that for now is just going to go for a sum k over the entire reciprocal lattice, not just b naught. Delta k to the d, 2 pi to the d, f bar k. And so then we also take after this, obviously, we want to get rid of the periodic boundary conditions by sort of moving them to infinity. So we take the infinite volume limit. L goes off to infinity. And so now these sums, obviously delta k is now going to go down to 0. And so delta sum over k in B naught, or just in B for now, delta k d over 2 pi d f bar k is going to go to the integral, and this is now going to be over all of real space of d dk 2 pi to the d f bar k. And likewise, our sort of box of integration for the real space sums is going to move out to infinity, right? So integral minus L over 2, L over 2 to the d dx f of x is just going to go to the integral over all of Rn d dx f of x. And we're going to sort of stop writing the Rn bit in there. We're just going to assume that all of our integrals are over all of space. Okay, now if we sort of go back and look at all of the various sums that we've sort of computed, then various things are important here. So first of all, phi of x is now, instead of a sum, it's an integral. d dk 2 pi to the d phi bar k e to the I k dot x. So any function of position can be thought of as an integral involving this function over momentum space. And likewise, phi bar k is the integral d dx phi of x, and we get a minus sign in this exponent from before. And then sort of two more things. The delta function, now 1 over a to the d delta x. X naught, well, in the infinite volume and or not really infinite volume, but just in the continuum limit where a goes to 0, this goes to the delta function. X minus x naught, the Dirac delta function. It's not really a function, it's a distribution, which has the property, basically, if you plug this into something, the sum of a to the d times 1 over a to the d delta x, x naught, f of x. The a to the d's cancel, and this is going to give you f x naught, right? Because that's the only place where the delta function is 1 instead of 0, or the Kronecker delta here. And so this whole thing is going to go to the integral over whatever box we're looking at. The a to the d becomes a dx to the d. This thing here becomes the delta function. We keep f of x the same, and we still sort of pluck out fx naught. This is sort of the defining function of the delta function. And we can also look at that sum we did earlier to say that basically delta x minus x naught is, by its sort of Fourier transform, the integral d dk over 2 pi to the d e to the I k dot x minus x naught. Okay, and finally our scalar product has also changed. So phi psi is now just going to become integral d dx of phi star x psi of x, or the integral d dk over 2 pi to the d phi bar star x psi bar x. Okay, so that's basically all of Fourier theory. We can sort of generalize to sort of, we take f subscript v, which now we're taking functions x into v, where v is a complex vector space, any complex vector space. And this is sort of not hard to generalize. We just sort of get new bases, fi x, which is going to be ui delta x primed. This is evaluated at x primed. And here ui I goes from 1 up to some number, we'll call it nu, is a basis of our new vector space V. And we also get sort of the reciprocal basis is f I k bar, evaluated at x, primed, why not, is ui, and then e to the I k dotted with x again, or x primed. And so we sort of have this, and we basically have just added in this extra vector definition. So our new dimension is the dimension of the vector space where we would just go into complex numbers times the dimension of the new vector space we're going to. And we get a new scalar product. So the scalar product on V dot V on V gives, we basically get on F, we're going to get sum over these x's in x naught, a to the d, and it's just f of x, scalar product in V, g of x. Sort of a fairly easy generalization. And this all just carries over really nicely to the integral stuff. And basically we just get phi j x is the integral d dk over 2 pi to the d phi bar j k e to the I k dotted with x. So there's no sort of mixing between these j components by the Fourier transform. No mixing of what we sort of call the internal space, because it's sort of the space at each point, V, due to the Fourier transform. Okay, and so that's basically everything. I think the only really important thing is that we should probably check really quickly why this is important. That sentence didn't really make sense. But what's sort of good about the Fourier transform? Why do we care? Well, when we look at sort of quantum mechanics, we have, for example, the momentum operator is I minus I times the partial derivative grad. Okay, and so for a general function phi of x, that's not really, well, it's easy to compute, it's just a derivative, but it's sort of not useful in that way. Whereas the momentum of e to the I k dot x is just k, right? Because we sort of differentiate and we're going to get down I k, then we have the minus I, that's going to get rid of the I, and we just get left with k times e to the I kx, right? So minus I grad e to the I k dot x equals k e to the I k dot x. And so that means that we've got things like the momentum operator on phi of x. Well, we can sort of redo this. We can turn this into an integral and then take the momentum into the integral. We're going to get d dk over 2 pi the d, and we just get a k in there as well. E to the I k dot x phi bar k. It makes this sort of thing much easier to work out. Okay, so I think that is everything I want to say this time, and I will sort of see you again in the next lecture, and we will continue sort of trudging towards path integrals. We're very nearly there now. There are sort of 2 things left, and that's looking at some sort of important bits on foundational quantum mechanics and the Schrodinger picture and the Heisenberg picture, and functional derivatives, and then path integration. So we're nearly there, and I'll see you next time.